I'm Eric Kreiger. I'm the structural lead for our construction program. So what we do is we do deployable construction, looking at researching deployable construction for the U.S. military, specifically additive construction. And so the reason for that is there's a lot of reasons. Essentially, it's that we want to be able to go to a location. We want to use locally available materials. We want to bring nothing but a machine with us and use those materials on location. And so essentially what we're doing is we're testing the capability to produce these structures in the field using locally available materials for on-demand, whatever we need. So think about what we have to do is we might have a mission. If we get a mission today, it's going to be like, okay, we need this in December. Whereas some missions, like space missions, it's going to be, we need this in 2028. And so our problem that we have is we need to be more agile, and so we need to have the solutions up front. And so typically when we go, we're limited, equipment is limited in availability. The construction process is short notice, short duration, and there's limited time for adjustments. Materials are brought to the site, so we want to use locally available materials, and those materials can be highly variable. We have seen, we've gotten aggregates that are we have lots of larger particles in those aggregates, and so in terms of incorporating those into our systems, which are limited to 3/8 inch aggregate, it's very difficult we have to come up with solutions on site. Transportation can be in months. We want to be able to shorten that as much as possible. We'll have limited transport availability, limited information, and limited design process. Basically, we need to come up with a design in a month or so. And so understanding how we test these, how we design, how we do all that, how we incorporate everything from understanding the mechanical properties to the fresh properties to the geometry that's required for printing to ensure that we don't get failure on site is critical for us to have mission success. And so I want to kind of highlight the timeline in terms of, starting off with, early concrete extrusion in the early 1900s to additive manufacturing starting in the 1980s we started some of the early work was in 2012 in terms of materials, and then we started in 2014. That was our first work was just, can we actually do this? There's some information out there, can we actually do it? And so within 2 years, we built the first house in the U.S. And so that was 2017. And then our second one was, and then we started producing walls for testing in the same year, and so I show the timeline here with kind of these projects that came out underneath, and I have highlighted in blue which ones were buildings, but there's other applications that we're looking at too, like bridges and infrastructure, but so kind of a compressed timeline here, and then we jumped to kind of 2020 and beyond, and then it became almost impossible because there are hundreds of different items that were constructed. And so we did anything from we did a post-tension gap crossing here. We did blast testing we deployed to Guam and did structures there. And then we also did a structure at Camp Atterbury, Indiana in 2023 and did blast testing for that too. And then we continue to kind of build things up. But one thing that we have been focusing on and what is kind of one of our primary now one of our primary missions in order to transition this technology, not only to commercial sector, but also for our use, is the development of codes and standards, because those are going to be what, you go to anybody and it's like, okay, what are the codes what are the codes and standards that we're going to follow, and that's the same within the Department of Defense. And so we had different workshops that we put on for internal to DoD as well as external. The external ones were in collaboration with NIST. So we had 2 of those, and we were looking to have others as well. But we produced a document called the UFC, and that provided information for the DoD for doing code level work. But that was very minimal. There's other efforts that are now ongoing that are providing language as well. So here's kind of an overview of where we've been. So the blue dots are where we've been for demonstrations, from anywhere from California to Missouri to our local area in Champaign, Illinois, all the way to Guam. And then we have partners within the different red dots all over the country. That's both academic as well as private sector. And then also DoD entities or governmental entities. And the reason for that is because we want to get over, there you saw someone showed the hype curve. In order to get over that trough of disillusionment, we need to make sure that we're communicating as a community with each other to basically feed off each other and understand what different aspects are, so that we can basically transition this technology and get over that trough. And so one thing that we do is that we do things in any conditions. We're not in a tent. We are outside. This is a picture from Guam. They had to assemble a printer in Guam. Sometimes it starts raining without any awareness. You don't see a cloud in the sky, and then it just starts pouring. And so they had to construct this printer in the field. They were able to do that. Our printers can typically be constructed within under an hour and then torn down in 30 minutes. And so it's very fast deployment. Take it out of the box, get it built, and then start going. But what we try to do is we try to push the limits in order to determine the worst case scenario. So the reason for that is we want to fail not We want to fail a lot. We want to get to where we need to go. And so when we started saying, okay, we're not going to start small scale and then build up. We're going to go full on in. We're going to use coarse aggregates. We're going to use large printers. Our first printer that we built was built within the first 6 months of the program. It was built with all scraps for like a ridiculous amount of money, it's like $5,000 maybe. It might have been less than that. But it was basically, we built it. It was 4 foot by 4 foot by 6 foot tall. And so we started looking at materials and extruding. And so kind of a brief overview, we do anything from internally as well as externally, working with partners, from experimental to design constraints to field validation to codes and training. So all except for the first building, all of our internal demonstrations have been, we train military personnel to do all of it. So we will teach them how to print, we will teach them how to assess materials. The only thing we haven't done is taught them design, and that's potentially coming. So, understanding mechanical properties, see a summary table of different mechanical properties. I don't know how hard that is to read, but essentially, same thing that's been talked all morning is anisotropy. If you were in the I know the mechanical one is overlapping, but they're talking about anisotropy over there. So understanding that anisotropy is important to the design aspects, but also if we're going to extract samples, we need to understand how to extract samples, how many samples to extract. Now, the current discussion right now is, can we get some relationship between cast and printed, and then utilize that relationship and validate that in the field, and then primarily use cast samples moving forward, because extremely difficult for someone to extract cast samples throughout the construction process. And then another thing is curing, cutting, how we're going to do that. Whether are we cutting, you know, in the fresh state? Are we saw cutting? Are we doing a combination of both? Is important. And so looking at the different aspects. And so we have, and if you haven't noticed, I show some of the publications. I'm doing a high-level overview because of the amount of work that we've done. And so if you're interested, I can provide those references. Oh yeah, as well as packaging. If we're doing larger samples, or if we're having samples cut, how do we do that? How do we transport those? That becomes a huge logistical issue, as well as interfaces. You know, some are thinking about roughening the interface, but what we've seen is that you get actually failures, bond failures, because you roughen the interface, and that's a huge issue. And then field testing. So we've developed field material tests. You saw the unconfined compression tests that people have shown, as well as the flow table. We've developed methodologies to do that in the field to evaluate materials, and so that the military personnel can produce those in the field. And then, so they're doing tests here, and then they can do, say, is the material good, yes or no? And then if that material is good, we can go ahead and use that. And that also includes coming out of the nozzle, from going into the pump to coming out of the nozzle, to just do some validation there. And then we also have kind of failure. So like if we're doing the unconfined compression over time, we can understand the curves and how the elastic modulus as well as the yield strength increase over time, and then we can do some failure curves to see, is it going to fail in either elastic buckling or plastic collapse. Structural testing, I'm going to kind of speed up a little bit, but what we've seen from structural testing is that if you're using the TMS or the masonry code or ACI 318, you're actually over designing by quite a bit for the demand, and the test results show that we can meet typical demand. Now, in some cases, you know, it depends on your loading conditions. So, what it showed is that traditional codes are not necessarily applicable to 3D printing, and so we need to understand how we design for these technologies. And then we've also done, by taking in the mechanical properties that we've determined, we've also done some finite element modeling using concrete damage plasticity and then traction separation law to describe the interfaces. And we've had pretty good results. We actually validated this model. We developed it using beams that we tested and then validated against the wall tests that we did, and we could predict that wall test very well in plane shear. And what we did is we did a parametric study to look at we used ANSYS, and we looked at the viscosity parameter as well as other parameters to determine what the best parameter is. And we've had good, and we're moving forward with that, and we're going to see, we've had pretty good predictions with that, but we're continuing to moving forward with some upcoming wall tests we're doing to see if that holds true. And then I just want to highlight some of these. I can't go over all these because of time, but we have a paper that was for Rylum, digital concrete in 2020, and it talks about lessons learned and issues that we've seen from a lot of our demonstrations, from equipment transportation, printer system, printing process, site. When you get on site, what are the issues? Environmental conditions, safety, and then materials in terms of like clogging hoses, things, and then being able to actually do the construction. So I want to finish with this video. So this is us at Camp Atterbury, Indiana. So we did everything from the foundation to the roof incorporates some form of additive construction, whether it's the formwork or the walls themselves, the composite walls themselves. And so you can see our material's much rougher than what you typically expect with traditional materials, but that's because we've determined that that's just an aesthetic aspect of the material. The strength is actually fine. And so because we're deployable and we want to reduce the amount of cement in there, we want to reduce the, we want to use large aggregate so that we can make sure that we're not using all that cement. It's not an issue for us because it's for a deployed scenario. And so we did a blast test on that to just look at what is the performance of our baseline structure. And then I also have, finishing up, I also have some tests here from Guam that we did different levels of blast testing on those in order to understand what are the dynamic effects. And so that's all I have.